Hi, okay, so this is going to be a code walkthrough of the function units, reservation stations, and the buffered pipeline that was being constructed. Now, where do I start? Okay, so this here is a book chapter written by Mitchell Alsop, who is the creator of the Motorola 68000. He studied the CDC 6600, and he's one of the few people who fully understands it, and he made some chapters, book chapters, which augment James Thornton's original book, Design of a Computer, which was written in the 70s, early 70s. And it brings, Mitch's modifications bring it up to date to modern pipeline stages. Now, what we've got here is a 4-input function unit, okay, where each of the inputs is effectively a reservation station if you're using Tomasulo algorithm terminology. And basically what it is it's a series of operand 1 and operand 2 latches with a multiplexer on it, where that is then put into a multi-stage pipeline, and the computational result goes out after a certain time delay to a result latches, which in turn then you select the one that you want to go on to the register. Now, to implement this, we have a couple of basic Python classes, which are NumEgen HDL modules. But the first one is we need a buffered pipeline system, and the second one is that we need a way to have reservation stations which can be told, which have your incoming strobe and will select on a round robin basis or a priority encoder basis one of the reservation stations to push through to the pipeline. Now, I took the original code from John Dawson, and that from the IEEE Floating FPU code that John wrote, and that has an acknowledge and a strobe system, where unfortunately what is required is that it will, if you look here, it requires that the ACK be high and the strobe be high to output, but it will then set the strobe to 0 and then raise it back up again once ACK has been set to 0, or if the strobe is in. So basically it outputs every alternate cycle, and that is not good enough, unfortunately. So we spent some time looking around for alternative code, and we came up with something. Alexander found this. It is something by Dan Gisselquist. It's an extremely good tutorial on how to do pipelines, and it goes from the basics first of all, where you just have a clock global valid signal and things move and transition, or every stage transitions, and the data will stay in the stage if things aren't moving. Right. That has quite a lot of latency, so he describes the next stage, which is that the clock enable, which is the thing, will travel with the data. Alright, so once you've got that concept established, if you can have a busy signal to say that a particular stage might happen to be busy, and you don't want to stop the thing unless it's absolutely necessary to do so. So you stall. I would say only if things are if the output is busy. Again, the problem with this is that you end up accumulating a lot of busy signals, and that's not a thing you get. They're all combinatorial, so the longer the stages you get, it all goes horribly wrong eventually. So the way that most things like AXI actually work is that you have traveling ACK and traveling strobe, which is acknowledged, and if the output happens to be busy, then on the next cycle it will the issue with these things is that you can't acknowledge the past. The data is ready from the previous stage. You can't go back in the past and say, hey guys, actually I didn't want you to send it because the output's busy. So what you have to do is you have to take responsibility. Your stage has to take responsibility, and it can say, I am busy now, don't send me any more, but it is absolutely required to buffer the input that it's just received, right? And at the same time, ready for the next cycle to say, hey, don't send in more until we process that. So that's what he calls the buffered handshake. And the nice thing about this system is that unlike John Dawson's system, it will receive and transmit data on every clock cycle, as long as it's ready and the input output is not busy. So there we go, the buffered handshake, and here we go, this little demonstration of how that works. So sharps. So that's what we implemented in Namigen. So it's really complicated, unfortunately, to understand, because you've got this input previous strobe goes to output next strobe, and the busy signal goes in the opposite direction. Input next busy, and you get as an output previous busy, and the data flows. So the strobes go from left to right, from previous stage to next stage. The busy signal goes from right to left to indicate busy, and the input data goes from left to right as output data. Now we've abstracted out. That's basically it. That's the key logic, and we've abstracted out the various stages so that we can use this for more purposes than just a thing. This is the whole reason why we're using Python. All right. So here is an abstracted function call saying we want you to update the output. So it goes here. If the input strobe is ready, we must process the incoming data and store it, and it gets stored in a temporary combinatorial block. If the if we are in the busy, if the previous stage, if we've indicated to the previous stage that we are busy, then you must put that combinatorial block into the Dan calls the a register, but it's just a temporary buffer. Anyway, it's complicated, and you can read the comments here in the that we've got. Here we've got the an example which it conforms to this new API, and this is the actual stage. Alright, so it's just a simple example where it adds one to the input data, stores it in the combinatorial block. Here's where the register is updated. If you're not in store mode, then the output data is updated from the combinatorial block, and if you are in store mode, then the register gets put through to the output first, then the stall is cleared, and on the next cycle you go back to processing results, which goes from this process function directly to the update output. So the input data processed. Okay, so I then wrote some unit tests. This is a very basic one, which you can see the signals here. So we have input data 5, 6, wrong file, wrong one, there we go, it's better. Input data 5, 7, then there's a clock, then a value 2, then another clock, then a value 9, then another clock, then a value 12, then another clock, then a value 32, 0x20, and another clock, and then clock. Right. So back to here. So there's the values: input data I_data 5, 7, 2, 9, C, 12 and 20, and as you can see, I've set the IN busy line. When the value is 9, I set the it to be busy, and that results in the output busy on the subsequent clock. It says so input next. Input next is the next stage. That it is an input into our current stage to say, don't send me any data. I am not ready to receive any data. And that gets propagated to O_P busy on the next clock, because you've got data coming in, which can't process it and say, hey, stop, start, sort of thing. So that's why the output data, as you can see there, O_data, stalls for 3 cycles. So you get 5 as input data is added 1, and on the next clock you get 6, 7 you get 8, on the next clock 2 you get 3, but because the IN busy input next busy signal is raised high for 2 clock cycles, during that 3 stays on the output for 3 cycles. IN busy is raised for 2, it gets set for 3 cycles, and finally it decides it gets released, but that value, the value 9, 0009 on the input data gets incremented to 10, and now you see the value 00C and 0020 do not get passed through to the output, and that is because input IP previous strobe, IP strobe, stops. I deliberately set it, IP strobe, to 0 to say, hey guys, the input data is not valid. So consequently, the outputting stops at that point, and that is why you see the value 0009 goes through delayed to 000A, but you do not see a 000D or a 0021 after it. Okay, that's what this is for. It's to get the ADC here. Now the next one that I did was I created a twin pipe, because I wanted to see what would happen if we had two of these pipes connected together. And sure enough, test bench number 2, we have test pipe 2, we have a slightly more complicated version which has a 2-cycle latency on when the output is the thing. So here, where in this one I'm doing check the output strobe line, I've had to delay that by another cycle and put in a few extra clock cycles. Alright. So the next step was to start using this. There we go. And send 10,000 random values into the pipeline. And here, so we set up an array of 10,000 values, and I wanted to do random stalling and random sending. So here we tell the input of the next stage. So the stage that is receiving this, we indicate that it is busy, i.e. that it is to stall for 1 out of 25% of the time this is to stall. Now the rules for this for sending data are that you can, if you want to send it, that is, send the data. So there's a 1 in 20% chance that we don't send data. So, but I made a mistake in this earlier. You have to leave, even if the output previous stage, even if the stage is saying it is busy, as in you mustn't send data, you must still put it on the input and leave the strobe high, so that when the busy signal goes low, the block can actually receive the valid data. Right? I made the mistake earlier of doing this. Unfortunately, what happened when I did that was that the valid data was lost, because the strobe went low when the busy signal was also went low, and that data was lost. So that is the correct thing to do, because it means that it leaves the strobe high and the data on the incoming bus. So we can only read the data. So basically you put one piece of data onto the input of the stage and increment the index and go on to the next one, but we don't go beyond the end of the list. That's that one. Okay, right. So this is the condition for when the data is valid, is when the output next strobe, when the output strobe has been raised by this thing, by it, and input next busy, and it's input next busy, and when we've set it is not busy, then that data is valid. So we yield. We're saying yield is the simulation thing for please give me the value. So we're checking the value from the simulation, from the NumIGen simulation. Here we're checking, so we're doing the calculation here in Python. Yes, I know the simulation is in Python, but it's hardware, but it is. So we're checking what the expected value against the simulated value, incrementing the thing, and then ending the simulation if the end of the data of the output index is end of the list is reached. And here we can see, oh darn, I can't do, hang on. Here we can see the some of the results going through. We've got the input data 00, 90, 91, 92. So there's a 90 of 1 clock, 91 goes through, 92, 93 for 2 cycles. So we've got a mixture of sending and also the strobe line indicating a busy signal combination of the thing. And after sending 10,000 values, managed to demonstrate that it's correct, which is fantastic. I then also did a 2-stage version. That's the 2-stage version. So I tested the double pipeline version as well. Right, that's down here. Just pipe 2 run testbench 4. So those testbench 3 and testbench 4 are identical code, except for the one comes from the stage from the local variable here. Software stage, which comes from here, and that's the thing. So basically, we've abstracted out the. That's not right. Yeah, that's better. Sorry. We've abstracted out the strobe input and output strobe and busy from the actual pipelining stage stuff. So that's the pipeline stage stuff, and to conform to that, to this API. But that's the only thing that you need to do. You don't actually need to know about the how the actual state, the pipeline strobe and busy stuff actually work. You just have to use it, which is great. Gotta tell you, it's as a complex as a state machine. It's really complex due to that buffering. So that is a component that can now be used. Let's go and have a look at the input group. Now, this is an implementation of this here, right? This part where the mouse is at the moment. And so that gives some. Let me have a look. So abstracted out the classes. Here is this. Here is basically the strobe on this is of width of the number of operations. Sorry, of number of operands. So rather than being just a single bit acknowledge of whether to proceed, it is a multi-bit. So it's ready. Strobe is ready when all bits are set to 1. So that's this is just a magic constant of 0x111111 binary, not xFFFF, of length of the number of bits. There's got to be a cleaner way to do it, but hey. So this is the ready is equivalent to a multi-bit strobe, and if the ACK and the strobe are both set, then we can just copy the all of the input operands into the output. Okay, right, but this is not yet doing the buffered pipeline system. It's the next stage. So here what we've got is a priority encoder, and the reason for using the priority encoder is to select one of those multiplex things to send to the output. So one of those strobes will be ready. Hey, there it is. Okay, alright, so we connect all of the ready signals of our inputs. Remember, there's multiple operands in here, but the ready signal only goes high when all strobe lines of those operands are high. And we're doing a bit of Python here, so we concatenate a list of all of those signals from our reservation stations, and then apply that as a tuple to the cat. That's a star args to a cat object, so that it's cat rs0 ready, comma rs1 ready, comma right. Then that goes into the priority encoder's input bits, and the job of the priority encoder is to give us a binary representation of one of those. We could do a round robin, alright, but decided to do a priority encoder just for fun. There's a whole stack of strategies we could do here. FIFO, priority encoder, round robin, they're all different things, so at some point we'll abstract that out. And here we need to know the ID of the reservation station which has been selected, because it's no good. We wouldn't know which one had gone through, and you'd lose all meaning. We need to know the index of the reservation station that we're processing through the pipeline. So it's an array, a horizontal array gets turned into a vertical input to a pipeline, one every clock, and then on the output again you turn it back into a horizontal input. So that's what this pipe thingy is here. That is the selector of the input and the output mux. So all quite simple. Let me see if I can show you the testing group IL uses read ilang test input group.il show top. There we go. Now I'm going to have to shrink this and bring it in. Okay, so here we have 4. I'm going to use zoom on here. Apologise, it will jump about a bit. So there we have the 4 reservation stations where they have, as you can see, each one has 2 inputs and 2 outputs, an ACK and a strobe. and an indication of ready bit, and the ready is high if the strobe 2 bits of strobe, both bits are high, then all those 4 ready bits get joined together. That then apologies, goes into our priority encoder here, and we get an active signal out, and we get a selector output which allows us to choose which one of the signals, prop group $group_9, which one of those gets passed through as the output. I like these graphs. As a rule, if it's not simple, if it doesn't look simple, if it looks a complete dog's dinner mess, there's something wrong with the code. So there we go. That's okay. It's a bit of a mess on the left hand side there, but that's just because we've had so many inputs. So yeah, the next stage is to take this input group and to create a modified version of the buffered pipeline to take a multi-bit strobe and to have a series of them, which is then an array of them that treat as reservation stations, and to then pass those through, have them the inputs acknowledged and passed through, because we really want it to be possible to have them buffer data as input, and not store. So yeah, it's complex, but it's sort of making all these little building blocks. It's quite a lot of it's quite a lot of fun. Really enjoying this experience. I've always wanted to do a processor, and I'll finally get a chance to do it. It's fantastic. Thank you very much.